and welcome to our Monday class. Again, early morning, 4 after 8. And what we're going to do before we hit it off, we are going to review some of the multimeters things. I know we're talking about those multimeters, but it's important that you are comfortable with using the metering equipment or the measuring equipment. So there's no problem. You can intuitively learn how to read the digital display because all you read is the numbers. And if something is wrong, the display is going to show you. Well, when it comes to analog meters, and sometimes you do want to use analog meters over the digital meters, simply because I'm going to demonstrate that for you. Let me just get the needle. Here's the needle. Okay. Let's say you get a reading like this. See that? Here is the needle swinging out. Okay. And if the voltage is whatever it is, it stays, digital meter is going to tell you and the analog meter is going to tell you. But if the voltage goes that way and it fluctuates like this, for example, and you need to know that, okay, or it stays there and just goes like this, or like this, the needle is going to show you and you're going to be very comfortable seeing what's going on. With the digital multimeter, you're going to have that thing trying to count up and count down, and it's not going to, you won't be able to make heads and tails. So sometimes, yes, you do want to, um, you do want to have a analog meter and just to see how things behave. So let's just swing out the needle to, let's say, here. Okay, here is our needle, and let's say we're going to where's our dial? Here's our dial, and we're going to set it to, let's say, DC voltage 50 volts range, which means we are measuring everything up to 50 volts. So are you able to tell, well, which scale you're going to? Let's take a look at some of the scales. So this scale on top here, the scale on very top is the resistance scale, and it shows the little omega sign right here. Okay, so if you were measuring resistance, this is what you would get. And look at that, everything starts at 0 on the left except for the resistance scale. The resistance scale starts on the right. What happens when you join, let's say you have those leads, red and black, and you join those leads together, what resistance are you going to have across those leads? Well, there's going to be no resistance because they are joined together, they are stuck together, they are touching each other, and they are both made out of metal. So the resistance between those two is going to be 0. So the needle is going to swing right up to here. Okay? And usually in analog meters, you're going to have, you see here, 0 ohms adjustment, right? So what's going to happen, let me just zoom out a tiny little bit, and let me get the needle here. The needle is going to swing somewhere around here when you touch the leads, all right? And it's not quite 0. So that's why the meters will have the little adjustment control that you turn to calibrate that, to make sure that, because the battery, internal battery could be a different strength or whatever it could be. That's why the analog meters will have the calibrating control that you actually bring that. By turning this, you're going to bring this to 0. But before you do that, what is going to happen is you're going to have that meter not connected to anything. All right. So the needle is going to be somewhere like this or somewhere like that. All right. What you're going to do is, here is a little adjustment knob or screw. and you just use maybe a 10-cent coin or tiny screwdriver. I think we have a storm here, and hopefully it's not going to knock us out. All right. Uh, excuse me. So mechanically, you're going to adjust that needle so it goes to that 0 point, and it's also going to coincide with that infinity um, indication on the resistance scale. So first, you're going to adjust that. So, oh, that's the wrong one. Needle here. And by turning that, you're going to adjust this to here. Right? Okay, so you have mechanically set things up. And then when you're going to touch those leads, the needle is going to have a full swing out. It's going to go to the 0 ohms. So it's going to go like, let's say this here. So that's when you use the adjustment knob, and different meters will have those at different places, sometimes on the side, so you can do it with your thumb, and you're going to bring that thing to the 0. So you get a proper reading. So first you calibrated that mechanically to have this thing at the 0 position for the voltage and whatever else, current and whatnot. And for the resistance, that's a little bit infinity sign, which is like a horizontal number 8. Okay, and then you're going to electronically or adjust this to the 0 position, and now you're ready. And now you are ready to now you're ready to do the measurements. Okay, let's say we're measuring voltage. So first you adjusted that to 0, just making sure. And one thing I'm going to tell you, this little gray area right here is supposed to mimic the mirror. Though the good ones, or pretty much all of them by now, meters, will have a tiny bit of a mirror right here, that little strip. The purpose of that is that you look at the needle straight, because the needle stands off a little bit on some height. And if you look at an angle, it's going to give you the angle view, so you might not see the proper reading. So if you look at it from the very top, and if you cover the image in the mirror, image of the needle, the reflection of the needle, if you cover that with the real needle, basically you adjust your eye with your angle, then you're looking at it straight, and then you can just tell whether the exact measurement, or where actually how far the needle exactly has swung. Okay, so let's say we have connected the leads to whatever the common, which will be the black, and the voltmeter wherever it's supposed to be in the meter, and we are measuring voltage, and we have set the voltage range to be 50 volts DC, because we're measuring, let's say, DC voltage. Right? And the needle goes, it just swung right here. Right? There you go. So we know that we have the range set to 50. Is there a scale? Let's take a look at some other scales. There is one scale here with the divisions, and there are some numbers. So this division is assigned to number 2, number 10, number 50. This division is assigned to number 4, 20, and 100, and so on. And over here, there's a little indicator showing that this scale is to be used with DC voltage and amps, and the little red scale is supposed to be used with the AC voltage. It's just how this particular meter works. Some other ones are going to have their scales arranged in a different way. You just got to figure it out, but you're going to look for the same common features. All right, so if we're measuring voltage DC, so we're going to use this division, this scale here. Now, which range we're at 50. Do we have anything 50 here? Yeah, oh, look at that. We have a 50 here. So what is the voltage that we are measuring? We're using the middle numbers, set of numbers here. 0, 10, 20, 30, 40. So here is going to be 30, 35. 1, 2, 3, 4, 5. So based on that, you can tell that each division in this case is 1 volt. All right, 30, 31, 32, 33, 34, 35, 6, 7, 8, 9, 40. Right here. Okay, so it looks like it's okay. So it's 35, 36, 37. Okay, easy, right? This measures 37 volts. Okay. But what if we don't have a scale that corresponds? Let's say there's a range of 100. We don't have 100 here. So now what I'm going to show you right now applies to all the measurements, pretty much all the, you can just use that method and you'll be comfortable. So let's leave the needle as it is. Let's leave the range as it is. So on this scale, because it's 50 and this is 50, so it's 1 to 1, so we're good. Okay, so but what if we want to measure the same voltage, same swinging out of the needle, and let's say if we get the same reading using a different scale? How do we use a different scale? We should get the same reading, right? Okay. All right. So let's say we're going to try to measure that same thing, but instead of using the 50 because it's the easiest, let's measure that with the scale of, well, 250. How can we get the same reading using a different scale? Well, 50 over 50, we had 1 to 1. If you go to a flea market and you buy a bag of potatoes or a bunch of loose potatoes, they are going to throw that on the scale. So this is the easiest way to remember. What do you do against? What do you divide by what? You throw the range, you throw things on the scale. So you have two quantities. You have the range and you have the scale. What do you do with the potatoes? You throw them on the scale. What do you do with whatever it is? You throw it on the scale. We throw the range on the scale. So you throw the range on the scale. Now get your calculators. Somebody get the calculator. So we are throwing the range on the scale, and the range is 50. Oh, yeah. The range is 50, and the scale is 250. Okay, so we throw the range on the scale. We don't throw the scale on the product. We throw the product on the scale. So 50 over 250 equals, can somebody give me a number? I know what it is. If you don't have a calculator, let's just go. 50 range on the scale divided by 250. And we're getting 0.2. There we go. Thank you. Thank you, guys. All right, so we got the 0.2. So that equals to 0.2, and that becomes our multiplier. All right. Now, there are two multipliers that we're going to be talking about. One is the multiplier that we're using with the analog meters to use the different scales. And the other multiplier is going to be that I'm going to introduce you to when we are going to do the pipe bending or the conduit bending. So we're also going to deal with something that's called a multiplier, but it's not the same thing as this. Right? So our multiplier in this case is 0.2. Okay, which means whatever the reading we get on that scale of 250, because we're using this the scale 250 with that range, we're going to have to multiply it by 0.2. So what is the reading that we get on the 250 scale? All right, let's see how the divisions work. So we got 0, we got 50. So that means somewhere in the middle, that is 25, 5, 10, 15, 20, 20. Okay, so it looks like every single division gives you 5 volts. All right, so we're on the scale of 250. So 150 here. We have 150. Okay, let me just get a different pointer. We have a 150 here, and we have 200 here, so 150. And if we just figured out that every little division is equal to 5 volts in this case, so 55, 160, 165, 170, 175, 180, 185. So we have one, we're reading 185 on the on the scale of 250, 185. So let's get 185 is the reading, and we're going to divide it by, sorry, we're going to multiply it, this is our multiplier, by 0.2. What do we get? All right, let's see, 185 not divided, multiplier, we multiply it, 185 times 0.2, 185 times 0.2. Oh, look, it gives you the same reading as 37 volts. Of course, it's going to give you this same reading. And if you use the same technique of throwing the range on the scale, you're going to get the same reading on this scale right now. That should work for the most part. Whatever scale you choose, sometimes you choose the scale that is most convenient based on just getting the calculations in your head. And sometimes you need to do a little tiny bit of calculations, but this is how it works. You can, if you do the same thing, you throw the range on the scale. So 50 over 10, 50 divided by 10. So you're going to have 5. So whatever you're going to get the reading, you're going to have to multiply it by 5. All right. So what is the reading that we get on the scale of 0 to 10? 6, 7. Okay, how is it? 7. That's 7, 7, 2, 4, 6, 10, 20, 30, 40. Okay, so it's 10, 7.2. Okay, so 1, 2, 3, 4, 5, 2, 4, 6, 8, 10. 7.4, 7, 2, 4, 6, 8, 10. That's gonna give it. So 7.4, okay, and multiplier is 5, so 7.4. 7.4 times 5. Look, it gives you 37 volts. It has to, because it's the quantity that we're measuring is the same thing. We're just using different scales. All right. So that kind of stuff is going to be on a test, but forget the test. Just make sure that you're comfortable with using those analog meters, because when you go to work, you will come across them. And well, it would be kind of funny if we let you out of the college if and you don't know how to use simple things like that. So just make sure, please, that um, that you learn how to do that. So once you go out in the whole wide world and you tell them that I was your teacher, then you're not gonna make me look bad. All right. Okay, cool. Let's get to the meat and potatoes that we're supposed to get right now. No, that's not the one that I want. Here, and let's start with this. All right. So first, let me just Control L, I think it is, to make it full screen. All right, first thing we're going to take care of is the supplement, and then I'm going to give you the main core of the lesson. Let's take a look at type of wires. One is a solid core wire, and the other one is a stranded wire. And by the way, all those notes are available for you to download, except I'm just making them visible to you after I do the lesson instead of before. I just want you to concentrate on what I'm talking about, whether instead of going through the papers while I'm teaching. Okay, so solid core wire and the stranded wire. Well, here is the picture of a solid core wire. It's one piece of solid hunk of metal, right, shaped into a wire and jacketed in a jacket. and clad it with a jacket. And then we have something that is stranded wire. Sometimes we want to use solid, sometimes we want to use stranded. Okay, so description, okay. Solid core wire is single strand or core of wire insulated with non-conductive material. Pretty simple, right? And as opposed to stranded wire, it's bundle of small gauge wires insulated with non-conductive material. Kaboom, kaboom. All right. So sometimes you want to have a stranded, sometimes you have to have a solid, and we'll go over that. Usage for solid, household and commercial usage, permanent mounting, permanent installations, and it's our typical of our in-wall power cabling or service cabling. Stranded wire. You can also use that in a household or commercial use. You can wire up your house with stranded. It's just going to be more expensive. All right. So you can use it in a household commercial. You can use it in a permanent mount, but because of the construction of the stranded, it's a bunch of smaller strands bundled up together. They don't carry vibrations as the solid core wire would. So that is the wire that we would use in the moving and vibrating parts, like wiring up, connecting power to a machine that works and vibrates and shakes and whatnot. If you open the hood of your car, you're going to have to look hard, and you probably won't find any solid wires. Always going to be stranded because well, the engine moves, it shakes and it vibrates. Okay, so for that reason, it's the typical industrial equipment cabling as far as stranded. Right? Advantages, it's less expensive to produce the solid core, of course, because the stranded, you have to make a lot of small strands and then you have to bundle them together. So there's that extra step in production. All right, household and commercial. Okay, wait a second, how am I taking? Advantages, it's less expensive to produce for the solid core, more compact in diameter for the same amount of current carrying capability as stranded would be. Right? Let me explain to you. You have to have a certain amount of copper to be able to carry a certain amount of current. If you don't have enough copper, if you don't have enough meat on that cable, it won't be able to carry as much current as it needs. So you need to have enough solid material, enough substance to be able to carry the current. Well, in the solid core, everything is nicely compacted or compacted. So it will take less space. When it comes to stranded, you also have to have the same amount of copper, but it's in the form of strands. And you can see those little gaps. It just takes more space to pack the same amount of copper in a stranded configuration than it would take in the solid configuration. Right? And also the solid core is less likely to fail due to corrosion. Well, the reason for that is you just have certain area exposed to the elements, and in here you have more area exposed to the elements. You have the area here, you have each little bit of that is an area, okay, and that is exposed to the elements. So corrosion would get this thing quicker than the solid core. All right. Disadvantages, typically available in small gauges, and we'll talk about that. Gauges is thicknesses, right? If you go um, um, in order to produce a cable or wire, it has to be somewhat flexible, and if you get this thing too thick, you are just dealing with a rod instead of wire, right? So it's not very practical to have extremely thick wires in a solid core configuration. So for that reason, a stranded cable is being used. And the disadvantage, continuous flexing or vibration will cause the wire to fatigue or break. So, well, because it's a solid wire, that's why you don't see any solid wires in a car wiring or any industrial machinery because it vibrates and shakes and whatnot. Now let's take a look at the stranded, what is it? Description, a bundle of small gauge wires. Small gauge, gauge is a thickness, so it's small gauge, but we'll talk about the gauge, all right? So take a look, just keep that in mind. So bunch of small thin wires insulated with non-conductive material, and we have usage. You can use it in household, permanent, moving, vibrating parts, typical. Now we'll have advantages and disadvantages. Advantages: very flexible and withstands a greater amount of flexing and vibration, and it's easier to route. So when pulling the wire through some pipes or conduits or around the corners and stuff, it's more flexible, yeah, because it's stranded, not solid. Then disadvantages: the diameter is larger for the same current carrying capability as solid. Same carrying capability or current carrying capability should be. It's more costly to produce. That's a disadvantage, as the manufacturing process is more complex, obviously. And then it's more likely to fail due to corrosion from capillary action and a high surface area. So basically, every single strand is surrounded by the elements, and the elements get to more area than here because it's just outside, and all this hunk of meat right here is protected by the surface of this whole thing, right? Okay, so here are the differences between solid and stranded, and this document is also available for you to download from the lecture, posted lecture notes. Why are homes wired using a solid rather than stranded? You can read that, or maybe I can just give you a little bit of heads up. Stranded wire is more expensive to produce. Okay, at a given wire gauge, stranded wire is going to take larger than solid. So yeah, okay. More area. It's going to take more space when you pull the wires or arrange those wires, install the wires. The main advantage of stranded is more flexible, so you generally don't need this in home wiring because it's all put in place once and hidden behind the walls, floors, or ceilings. The house does not vibrate just like car would or a machine would. If it does, then you're in bigger trouble than this. When you screw a solid wire into a switch receptacle, so if you use a screw terminal, you can tell it's secure. I could see individual strands coming loose. Okay, read that. I know I wrote it, and I just don't want to read it. You read it. Okay? I explain everything. Now here's some references that I actually have to provide because I use some materials from the internet. Right, there we go. Close that. Now let's get to this right here. Control L. And we have types of wires. Let's take a look at this here first. Some of us already participated in the lab 1, when we were dealing with something that's called NMD90 cable. And we're giving you, during the lab, we're giving you a little tiny bit of a kind of a lecture, but not, it's just like a preamble for the lab. So half of us already were able to familiarize ourselves with, and the other half of the class is going to play with those wires this week in the lab. How do we look at those wires? Okay, excuse me. All right, we have a little wire here, and this one shows 14.2, and this one shows 14.3, if you can see that. All right, here's a cable that says 2-wire cable, and here's a cable that says 3-wire cable. Let's count the wires. As I always say, there are 3 kinds of people in this world. ones that they can count and the ones that they can't. All right. Let's see, 14.2, it says 2-wire cable. Let's count the wires here. 1 and 2 and 3. So everything is good. It's a 2-wire cable. It has three. It's a 3 wires, and that's why we call it 2-wire. All right. So here's the idea when we designate when we come up with the designations for the cables. There are current carrying conductors, and there's one safety conductor, grounding or bonding conductor. First of all, what is the difference between grounding and bonding? Let's say there is a grounding strip somewhere here on this panel. Right? I know it's somewhere there. And this grounding strip is connected with a solid wire that goes somewhere outside of the house, and it is connected to a true ground. I'm trying to find that grounding. I can't find it here. Grounding bar here. Anyways, so if there's a wire that goes straight to a true ground, what is a true ground? A true ground is well, it could be a metal plate driven into the ground outside of the building. It could be a spike driven into the ground outside of the building, or it could be in the construction, provided by the construction, there could be a bar that is in the electrical room that it says this is the true ground. So then you can tell that this electrical panel is grounded. Now, from all the circuit breakers and from the grounding strip right here, wherever it is, it looks like this one here, but I can see white wire coming into it, so that couldn't be it. So there's a grounding strip somewhere here, grounding screw. So from that grounding strip, from this panel, there is a grounding wire that goes everywhere else in the household. For example, it goes to one receptacle, from that receptacle goes to another receptacle, and from that receptacle goes to another receptacle, and so on. You get the idea. And the grounding or bonding wire is either a bare copper or it is a green jacketed cable. So I can see a bare copper conductor here, and I can see a green jacketed conductor here. So they're both grounds or bonds. Right? Now, when that bare copper wire or green jacketed wire, this is the standards in North America. In Europe, they might be a little bit different, but if you work there, you're gonna have to find out. I'm going to give you too much of it today. If the grounding wire goes from this panel into the receptacle, that receptacle is pretty much electrically grounded, but because there is no straight, uninterrupted, solid or stranded wire, goes directly through the true ground, then we call that receptacle bonded. You can see the receptacle bonded, say that it's bonded instead of grounded. It's still electrically grounded on the same potential as ground, but physically there is no one uninterrupted wire going from that device to true ground. It goes through the electrical panel and then goes to the true ground. That then we're calling that bonded, right? Same thing, ground or bond, electrically the same thing. You get the idea. Okay, I can see here. Who can see your messages? Recording on. Recording is on. Is it? If I go more, it says stop recording, which means it is recording. I don't have the message, the option to start recording. Okay, so and the other two conductors in that cable are current carrying conductors. So the white and the black, for example, here in the, oh, it's kind of blurry. The white and the black in this 14.2 are current carrying conductors, which means under normal conditions, these are the wires that are supposed to conduct current, and the grounding or bonding wire is supposed to act as a safety. It is supposed to carry the current if something goes wrong, so this is supposed to take the hit instead of you taking the hit. Excuse me. So that's why we call it 14.2, because we only count the current carrying conductors. We don't count the bonding wire. So 14.2. What is that 14? The 14 is something that's called a gauge. The gauge determines the thickness of the wire. Right? And just, well, you're going to have to remember that, and I'm not going to get into the historical side of how the gauge became a gauge. It basically had, well, believe it or not, it started with firearms, with shooting guns or shotguns. That's how the gauge became gauge, and it comes from kind of like a well, from England, or Great Britain, that somebody decided that there's a certain amount of container, and let's see how many lead balls can you fit in that container, and that is going to be the gauge. So let's say 12 gauge shotgun will fit 12, well, 12 gauge shotgun, so it's going to fit so many balls of certain size into that container or the diameter, and that is going to be called 12 gauge. So that's why the gauge becomes. So if you can fit more of the balls, then the balls have to be thinner, smaller in size, so you can fit more of them in the same area, so the gauge is bigger. And if the balls are bigger, then you can fit less of them in the same area, so the gauge is smaller because smaller amount of them can be fit in a certain area. So that's how the gauge becomes. So the gauge talks about the thickness of the wire, and for that reason, when the gauge goes up, the thickness of the wire goes down. So the higher the gauge, the thinner the cable. They are inversely proportional. One goes up, the other goes down. If the gauge number goes down, that means the wire is thicker, right? So just, and the gauge is presented in something that's called AWG. So there'll be number and AWG, and AWG stands for American Wiring Gauge. But if you talk well, during the normal talk, you're not going to say, can I have 14 American wiring gauge wire? Because you're going to have to repeat that thing a lot. So just a gauge. When you see the AWG, you read it as gauge. That's how we spell gauge too. All right. Also, in the sense of also. All right. So and you'll see how I'm going to read that. All right. Now here's a 3-wire cable. And you can see 14.3, so that you can tell that it's 14 gauge, certain thickness. It is the common household wiring, the 14 gauge, and it's a 14.3 because it has 3 current carrying conductors. It has the um, bonding wire, which we don't count, and then we go white is the neutral, black is hot, and red is the other hot. White is the neutral, and the neutral is pretty much supposed to be at the same potential that the ground is, or the bond is. So if you put a voltmeter between the neutral and the ground or bond, you should pretty much not get any voltage on that. you might get a little tiny, like a half a volt or a quarter of a volt or something, and that's going to be caused by the general noise that's in that's in the wires. Uh, but if you get like 14 or 15 or 20 volts on that, then something is wrong. Okay? Now, how is it that we're going to distinguish those wires? Okay, so we know already that the bonding wire is the bonding wire and it's a safety wire, and under normal circumstances it doesn't conduct. It's supposed to be able to conduct, but under normal circumstances there's no current flowing through it. Those two current carrying conductors are the white, which is neutral, and the black, and it is hot. So we need to complete the circuit. If you have the neutral, you're going to come out of the, let's say neutral is the return path. So let's say the hot, here's a hot wire, which is black, and you're going to go to a load, go through a load, and come out of the load, and you're going to close the circuit, returning the current path to the white, which is the neutral. That's basically how, in normal circumstances, the current flows. If something goes wrong, then the bonding wire should take the hit, not you. What could go wrong? Let's say you have a metal enclosure, metal box that there's a receptacle in, or a switch in, or something. And then for some reason, let's say that the hot wire gets detached. It gets detached from the screw terminal and it touches the metal box. Well, if there were no mm, bonding wire bonding that electrical box to the ground, then because the hot wire touches that metal box becomes hot. And if you touch that with your hand and you're standing firmly on the ground, or touching something else with the other hand that could be connected or close to ground, then the current is going to flow through you um, from the box to the ground through you, depending on, well, and it's going to take the shortest path. So it could go through your chest, that's where your heart is. It could go through your stomach, that's where your stomach is, and the stomach acids and all that stuff. And what happens when you pass electricity through acids and a whole bunch of chemistry? You get a breakdown to different chemical components. So um, in extreme conditions, you could actually get poisoned by being by having electrical shock, and you're not going to die right away, but it's going to take you a few minutes, right? So I'm not trying to be funny here, but you just have to keep that in mind, and that usually happens with the DC voltage quicker than the AC. So that's why we need to use the bonding wire. So what we do is we connect that bonding wire to the grounding uh, terminal in that metal electrical box. So that metal electrical box is grounded. It's not just hanging in the air. So when by accident the hot wire detaches from the screw terminal and touches the box, the electricity is going to be drained to the ground through the safety or the bonding or the grounding wire, and well, probably is going to flip the circuit breaker. It's going to open the circuit breaker, and then that's why this is, now of course there's no guarantees to anything, but this is how it's supposed to work. Current carrying conductors, there's a safety or grounding wire, bonding wire. All right, now we have 14.3. What do we have? We always have the ground, which we don't count. So that's we have 1, 2, 3 current carrying conductors. And again, I'm going to repeat, what is a current carrying conductor? A current carrying conductor is a conductor that is supposed to conduct or carry current under normal operating circumstances. You plug something in, a vacuum cleaner, a tea kettle, TV, radio, light, or whatnot. Now, the neutral is always white. Then the first hot is going to be white, sorry, the black. Black is always hot. And then the red is always hot. So that's 14.3. All right, now then we have, this is something that's called an NMD 90. NMD 90. Well, we're going to talk about that. which stands for non-metallic, dry, and it's supposed to withstand conditions up to 90 degrees Celsius is rated for that. Where does the water boil as far as Celsius temperature? It's 100 degrees Celsius. So it's this jacketing of that, the sheeting here, the cladding, it is supposed to withstand and not get damaged if the temperature reaches 90 degrees Celsius. If it goes over, well, funny things can happen. We're going to leave the fasteners for now because they are just, well, there's so many fasteners. I'm going to keep introducing you to the fasteners and connectors as we go along with the labs. Same as that, well, red eye or anti-short bushing when it comes to armored cable. Here's a 2-wire armored cable. Here's a 3-wire armored cable. And it is, well, sometimes it's referred to as BX. And where does the BX come from? The BX comes from when there was a company that was developing this type of wire or cable. They call it, they were in the experimental stage, so they call it cable B experimental. So BX. It's not really referred to as in the electrical code, but if somebody says BX, then this is what it means. And of course, here is a 2-wire armored cable. Here's a 3-wire armored cable. And sometimes you will get the bonding wire with it, and sometimes you won't. All right. UF cable. When you say when you see the UF, that means it's an underground feeder cable, which means it can be mounted. It could be installed underground. There is also sometimes you're going to see a little designation that says B UF, for example, something B, then that means it could be installed as a direct burial, which means you don't need any additional structures to support that. You can just put that in the ground as it is on its own, and it's designated for that, it's rated for that. All right. Now, gauges, as you could say, 10 gauge or 12 gauge. 12 gauge is thinner than 10 gauge. So the gauge goes up, the thickness goes down. And the gauge goes down, the thickness goes up. So that's what basically, here. All right. So this is basically what I said here. Um, Household wiring and cables. Let's say here, single conductor wires. Here's a solid core and stranded. We went over that. Here are multi-conductor, NMD 90. So the NM normally says non-metallic sheeted cable 12-2. What does that 12-2? It says 12 gauge and 2 conductors. So the 12 gauge is a thicker cable than 14 gauge. Okay. And it says 12-2, which means 2 current carrying conductors, and the grounding wire or bonding wire is not counted. So that's why we say 2, right? So here's the jacketing type of NM, non-metallic. That means that the jacketing is non-metallic and it's supposed to be installed in non-metallic environment. So when you go to a framing, you would install that on a wooden framing or anything that's non-metallic. But if you have a metal studs or metal framing, you're not supposed to use that cable directly. That's in a way that it touches directly the metal framing. Sometimes it is you could see that if somebody really wants to do that, they would put like a little 2x4. They would mount it to the frame, to the steel frame, and then they would mount the cable to the wooden 2x4. Uh, but normally you would get either the armored cable when it comes to steel frames, or you would get pipes or conduits if you really want, and you can put that in the conduit, and then you can have that installed in the steel frame. Type non-metallic sheeted 14.3, okay, 14.2. So again, We are not counting the grounding wire or bonding wire. So 14.2 or 12.2 is a thicker than 14. 14 is a thinner cable. 14.3, how can we tell? Okay, so 14.3, what can we tell by that? It's a gauge, it's a 14 gauge, which means it's the thinner cable than the 12 gauge. And there's three, that means three current carrying conductors. We don't count the bonding wire. And here is for large appliances. You can see if there's larger cables, there's a tendency of using stranded cables. Large appliances cable for dedicated 120 or 120 volt circuits. Stranded wires that are bendable, but well, barely. um, okay, type of MC. Um, that's the armored cable that we talked about, and we're going to talk about a little bit. Well, I already gave you the MC stands for metal cladding, metal cladded. So cladding is a surrounding, right? So sometimes it's called the MC, sometimes it's called the armored cable. There's slight differences, and you can hear on the construction side that someone's going to say BX. Same as for the NMD90, sometimes you're going to hear the term Romex. Right? What does the why is it called Romex? Well, that cable some time ago was exclusively produced by a company that is called Romex. Excuse me. So that's why sometimes you still will hear get some Romex cable installed here. But that means it's NMD90. Gauges, that's what I was talking about when it comes to gauges. 14 gauge, 12 gauge, 10 gauge, 8 gauge. See, the gauge goes up, the gauge number goes up, the thickness of the wire goes down. The the gauge number goes down, the thickness of the wire goes the other way, right? So I might ask you on a test, does the solid cable come in all different gauges? Well, does it? Well, no, because if you go very thick with the cable, you're talking an inch thick, 2 inches thick, or whatnot, then it's just impractical. Yes, sometimes you can get a special order I've seen it. I've seen an extremely thick cable that was solid, and I don't know how is it that they pulled it, how is it they installed it. Was an immaculate, nice, beautiful installation, and it was solid. It's a solid cable. How did they do it? I don't know, but for the most part, generally they don't come in all different gauges. Solid wires do not come in all different gauges, simply because if you go thick enough with the solid wire, you are, as I said before, you are dealing with a metal rod instead of a conductor or a wire. Right? Um, okay, so what I'm going to do is, if you have another class, please go. This lesson is recorded, so if you're willing to stay, we're going to go maybe 5 or 6 minutes over the time, and you can catch the rest of it on YouTube as I post it. All right. So household wiring, it's the most common, and I'm going to read some of that. The most common type of cable used in houses is technically known as the NMD90, and the NMD90 stands for non-metallic dry service cable. What's a service cable? It's a cable that provides power. What could we have other than service cable? Well, we could have signal cable. Like for the microphones and so on, speaker cable, whatever. It's so, but service cable is a cable that provides power. So NMD90 stands for non-metallic, dry. You're not supposed to have that thing regularly exposed to moisture. So in the walls, you're not supposed to have moisture. If you do, you have a bigger problem than that, as I said before. It's a service cable rated at the maximum of 90 degrees Celsius. It's supposed to withstand 90 degrees Celsius. Water boils in 100 degrees Celsius. So it's pretty close to boiling water. So that's pretty hot. You won't be able to withstand that. You can't touch 90 degrees with your bare hand. You're going to get burnt. excuse me, the brand name that is commonly called as Romex, which I just explained. The cable is usually configured in 2 or 3 conductor combination, the conductor having a black and white conductor and the bare copper wire. The bare copper wire is never counted when the conductor in the conductor count, which I explained that probably extensively in the last few minutes. Three conductor has 3 conductors. So let's say whatever three conductor has a black, red, and white conductor and a bare copper wire. So it has 4 conductors really, but we're just counting the current carrying conductors. The conductors are most commonly the conductors are most commonly as 14, and you see American wiring gauge. When you see that, you just read gauge, 14 gauge. Um, you don't read number 14 AWG, or if for sure you don't read hashtag 14. Okay, so this is just skip that. It's just 14 gauge. All right. The cable also comes as 2 and 3 wire in 12 gauge configurations, depending on if we need more current to be passing through the cable, you use well, thicker cable, which you go down with the gauge. Right? Household wiring, most commonly used cables in and their uses. Two conductor 14, so it's 214. It's mostly used plugs, switches, lights. It takes about 70% of your regular household wiring, and that's what the cable looks like. All right, 314, all right, or 14.3. It's used for three-way switches, and we will go over what the three-way switches are, and we will also go over what split receptacles are. We're going to give you that little bit of rundown during the labs, and I'll cover that on the in some theory classes as well as we go along. Continuing, 214 selected heaters. Sorry, we're going to 12.2. See, it's a you see 14.2 is mostly plugs, switches, lights. All right. 14.3, so 14 gauge switches, split receptacles. It's a regular kind of a medium light duty usage. So you can plug in a vacuum cleaner, TV, radio, a light, even like a soldering iron or a toaster, whatnot. Okay. Now, so it's 14 gauge. Now look at this. Here's 12 gauge, which is a thicker wire, which is supposed to carry more current. So here's a 12.2. It will be selected heaters. Heaters take more space, more current. Air compressors, anything that uses a maximum of 20 amps. Kitchen receptacle circuits as well. 3 conductor, okay, so 10.3, any device that requires a maximum of 30 amps. And 1 amp, an amp is a unit of current. So you see here, 14 is rated for 15 amps, 15. Then gauge 12 is a thicker wire. It's rated for 20 amps. Then we go down with the gauge, which the wire becomes thicker, and you go 30 amps. And then we go even thicker wire because it's 8 gauge, then maximum of 40 amps. So here's how here's how it goes. So if you have a piece of wire running in the or conduct or cable running in the wall, and let's say it was 14.2, and you need to connect an air condition to it, then you could be out of luck a little bit because you need 20 amps for air conditioner. Excuse me. So what do? You go and replace the circuit breaker for a bigger one. Let's instead of 15 amps circuit breaker at the electrical panel, you would put a 20 amps circuit breaker, and you would install an outlet that can fit, or the receptacle that physically fits the 20 amps plug that comes with the air condition unit, which is that one of the prongs is kind of like sideways. Well, and then you're good, right? Well, wrong, because you still have that wire in the wall that is not thick enough. All right, so don't ever do that. That's how fires started. That's how fires start. Household wiring. Now, is household wiring wired in series or in parallel, or depends on the code, or using wires dummy, whichever way is easy. Right? How is it that the household wiring is wired? Okay, well, we already know what the difference is between series and parallel. Um, let me start a new page here. Okay, so now we know what the series is, right? So let's say here is a hot wire, here is a neutral wire, and here is the ground. Okay. So let's say if we wire that in series, we would go to one receptacle and then to another receptacle, right? And then we go to another receptacle, and we're just going to bring it back to the neutral. So here's the current way. So this would be series. Okay, well, let's say that to this outlet we plug in a TV. All right. And let's say to this outlet there is a vacuum cleaner. Right. And let's say to this outlet there is plugged in a fridge. Right. Well, what happens is that in the series, if you interrupt the circuit at any point, you are going to interrupt the whole current flow. So just like the Christmas lights, the old Christmas lights. Um, mm, if you take one bulb out, the whole thing goes down. So if the household wiring was wired in series, in order for you to have the fridge working, you would have to have the TV on and the vacuum cleaner, and then the fridge works. So that's not very practical. So no, that would be serious. Now let's go to parallel. Parallel. All right. Parallel. Okay. So here is hot. Here is neutral. Here is ground. Okay. So we just go and extend the wire there. So here's an outlet. Here's an outlet. Here's an outlet. Here's an outlet. Dum 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 dum. Okay. Let's make them look like an outlet. And we're going to connect those outlets like this. All right. That's in parallel. So you can plug in anything to any of those outlets and it can work on its own because it's always connected to the, if nothing is plugged in here and you plug in fridge to this outlet, yeah, then the fridge doesn't have power. Yes, it's connected to hot, and on the other side is connected to neutral. So the current will flow from here through the fridge and back to the neutral. Right? So that's why the household wiring should be done in parallel instead of series, and all the other two are just wrong answers. Right? When you download this, I want you to just go and take a look at and find out and just kind of look through it and see if you can find the elements that I was talking about during this lesson. So here's the grounding, here's a light switch, here is the ceiling. So just go through that, and we're going to review that next time we see each other. Service conductors. One more thing, I need you to understand this. Service conductors. There are specific cables used to carry the power into the house to the service panel. These are referred as service conductors. So service conductors provide power as opposed to signal wires, like there will be like a microphone wire or cable. So let's give out service conductors that are run overhead are generally made out of aluminum, or if you're from England, you would say aluminium. I don't know in Australia. Now, to reduce the weight of the cable, right? Generally, copper is the mm, better metal to for the current carrying conductors. Why is it better? Well, for the most part, it's not deteriorating as aluminum would. Aluminum wires over time, they heat up and they just lose their weight. They become thinner. It takes a long time for them to become significantly thinner, but they do. Mm, And copper is generally a better conductor than aluminum. However, if you carry the wires overhead, which would be from the service demarcation point here, and it's overhead, just hanging overhead, it goes to the hydro pole. That's where the transformer lives and whatnot. It's overhead, it's hanging, it weighs. So aluminum, although it's not the better choice as far as conductivity and current carrying features, it is lighter. So that's why aluminum is used for hanging or overhead conductors. And that is the last slide. I'm just going to open the floor for any questions for a couple minutes. We went 9 minutes over time. And if there are no any questions, I will see you when I see you. Okay, I'm just going to stop sharing the screen. Here you go, my big face here. Okay, no questions. Thank you very much. And I will see some of you during the labs, and I will see some of you later on this week on Friday. Okay, have a good week, guys. Thank you very much.